Welcome everyone to this week's Space Science Seminar. Today we will hear from Professor Ningyu Liu. Professor Liu is a professor of physics and astronomy here at UNH with a joint appointment in the Space Science Center. Professor Liu received his PhD in electrical and electronic engineering technology from Pennsylvania State University. And he's published extensively on electrical discharges in Earth's atmosphere, like lightning, jets, and sprites. Today, Professor Liu will discuss ultra-wideband radio frequency lightning interferometry with RIFTS. And with that, welcome and thank you very much.
Perfect, thanks. First, before I start, let me thank Jason and Evan to organize this Science Center seminar, also for the invitation to share our research with you. And we have been working on RIFTS for 4 years, and it has been an exciting project. It's the first instrumentation project, a serious instrumentation project I have worked on, and certainly it's a lot of fun. At the same time, we ran into a lot of challenges, but eventually I think we made it work. So the background image on the first slide here is the antennas we deployed at the field site next to the UNH observatory. And today I will show some results from the first storm we observed using RIFTS. And before I start, I want to acknowledge a lot of people who have worked on this project, including Space Science Center faculty Joe Dwyer, Hollis Benz, and also engineers Evan Dawes, Dan Abel, and Arlo Johnson. A lot of students have contributed to this project too. Stephen Hall, who is a computer science graduate student, and we also have other graduate students. And particularly, I want to emphasize the contribution from a few undergraduate students, including Anderson Stegler. He worked on this project for about 2 years, who really did excellent work on. We did a lot of hard work to deploy the instrument or lay out the cables and also characterize the cables, delay or response. He did excellent work and he wrote a senior thesis on this project. Another undergraduate student is Angus Kirkpatrick. He also wrote a senior thesis on this project. And then we currently have 2 undergraduate students, Josh and Jake. There's 2 students who are doing senior design projects on this. So I'm very happy that we were able to support the training experience for our undergraduate students here. And my co-PI Franklin and his team at MIT Haystack Observatory really are expert on radio instrumentation. So we got a lot of help from them. And also Mark Stanley, who is an expert in lightning radio interferometer and also field experiments. I also want to thank the Space Science Center who provides partial support to this project. And John Forte, who is the director of the UNH Observatory, and we got a lot of help from John and his students, and because we use a field site next to the observatory, and also Kevin Computer from COLA, they help us to fund this field site, and also UNH facility people. Okay, so everyone is familiar with lightning, and you may be wondering why we are still studying lightning. And let me start with showing this video. So this is a lightning storm back in 2016 when I was still in Florida. And so we are watching a storm very close by. It's about maybe 3 kilometers away. And we're looking at the cloud base. And so we have cloud to ground lightning flash. As you can see, as the lightning exits the cloud, it branches. A lot of flickering, very complex in terms of the spatial and temporal behavior. So you can see it's a very complex phenomenon. From just from the optical images, it's just very difficult to to detailedly investigate the properties of lighting. And especially if you want to look into what's going on inside clouds, if you, for example, want to understand how lighting is initiated, then the optical instruments, of course, don't work because we cannot see through the cloud. Then what can you do? Well, you can use radio instruments because lightning can generate broadband radio emissions. So what you are seeing here are the recording from two sensors. The black curve is recorded by a sensor sensitive to long wave bands with wavelengths around 1 kilometer, or from it's actually broadband from VIF wave to HF wave. And the blue traces is a sensor that covers VHF band, so the wavelength goes from 1 to 10 inches, for example. Then this is a cloud to ground lightning strike. So the lightning initiated around this time, then within 30 milliseconds, it went to ground. And you can see, it generates a lot of stuff. And if we zoom into the first 2 milliseconds, this is the bottom panel here, then you can see, you can tell some bursts for the VIF to HF broadband sensor, we have those pulses. And if you ask someone who is working on lighting research for a while, they will tell you, wow, this is the initiation stage of lighting. So by looking at these pulse shapes, we can know what is going on inside the cloud. And then for the blue traces, this covers the VHF frequency range. And you basically see some noise-like signals. Okay, so this is from one sensor or two sensors. But if you have more sensors, more of the same type of sensors, let's say we have 3 of those VHF sensors, they're labeled A, B, C here, then you can make a radio interferometry. So then you can use those 3 sensors to record the signals from lightning, and then combine the signals, that you can get more information about the source of the radiation. So we can get more or better information about the lightning events. So this is a system we used back in 2016. The system was developed by a lighting team at New Mexico Tech. It has 3 sensors, as I said earlier, and each is digitized at 180 megahertz. And each sample is like 2 bytes or 16-bit. Then if we multiply this digitizing frequency by 2 bytes by 3 sensors, then the data reach we're looking at is like 1 gigabyte per second. So in order to study lightning, this is the data reach you will need. Very fast, high throughput data system you will need. So, but then before I talk about our instrumentation, let me just give you an introduction about how we combine those signals so we can get more information about source. So we typically use a cross-correlation based interferometry method. How it works looks like this. So suppose you have 2 sensors, and B, and they're separated by a distance D. And typically the lighting source is far away. So when they arrive at the sensor, you can consider the wave is a plane wave. And then with a plane wave, the difference, the time difference of the events, the lighting events arrive at those two sensors will be determined by this distance here. Then let's say the time delay is tau. This tau is entirely depends on the angle theta. So with different angle, then your delay will be different. So if you are able to measure this delay, then you are able to infer the angle theta. This is the direction angle with respect to baseline AD. If we have three sensors, we have three baseline. We have AB, AC, BC, then we have three baseline. Then for each sensor, you will record, let's say, some waveform like that. So we have three waveforms. There's a delay between them. Then the question, how do you get that delay? So you can use cross correlation to do it. So you do the cross correlation between two waveforms. Then when you do that, you get something like this. Then the peak of the cross correlation will tells you the delay between the two events arriving at the two sensors. But then that delay corresponds to an angle. So you can, instead of cross correlation as a function of delay or time, you can represent that correlation as a function of directional angle. Then we have three baseline. We can have three of those cross correlations as a function of directional angle. When you combine them, you can simply just add them together. You can construct an image. So this is how radio interferometry imaging works for lighting studies. So it's very simple, mostly just geometric stuff. And then suppose you have a very long recording, you can chop the recording into small intervals. Then for each interval, you can get an image, and this is what is shown here. For example, for the 0.3 microseconds, we get an image. Then after 4 microseconds, you get another image. So you can tell where the source is and how it moves. And the size of this we call the main lobe determines the resolution of the instrument. That size is determined by the wavelength divided by the baseline length. If your wavelength is shorter, your resolution will be better. If your baseline length is longer, your resolution will be better. So for the instrument we used in 2016, the resolution is 3.5 degrees. And if at 10 kilometer distance, that's about 600 meters. Okay, so if you do that, and then just observe lightning and chop your recording into small interval. For each interval, you get a source. Then you plot that source on elevation versus azimuth angle. You can get animation like this. This is like, imagine you are watching a distant sandstorm, maybe 20 kilometers away. There's lightning activity inside the storm, and then the lightning activity continuously emits RF radiation. Then you apply the interferometric imaging method. Then you can map the lightning propagation or network. Okay, so it's very, very detailed, and but at the same time, because the instrument, the baseline length for this case is like 100 meters. That 100 meter length is relatively short compared to the distance to the storm. So we can only make 2D images of the lightning instead of 3D. Now, our UH lighting team, including Joe and also some of our students, have been working with a team in the Netherlands to use LOFAR to image lightning. And the LOFAR is a large radio telescope. They have thousands of antennas in Europe. And so far, we have been using about 200 antennas in Netherlands itself to image lightning. Then with that, so those numbers here represent the station. So you can see now the baseline length is very, very large, and then we can get this 3D images of lightning flash. And this is one of the animations they created by using LOFAR observation of lightning flash. So now we have 3D structures. And in terms of location accuracy or uncertainty, LOFAR is certainly the best. They can get down to the 20 centimeter-ish location accuracy. Okay, but It doesn't mean for other lightning instrumentation groups, there's no work to do, but you can still design your own instrument, which you can, for example, make it flexible, make it deployable, and also for LoFar. So far, it only covers a wavelength range or frequency range from 30 to 80 megahertz. We can, because lightning can emit signals with higher frequency, so we can make instrument with broader bandwidth and also make it flexible. And this is the purpose of RIFTS. RIFTS stands for Radio Interferometry for Sandstorm Studies. The name, Joe coins the name. I really like the name, and I think our whole team really likes the name. And so the idea is we will have more elements. So we will have 8 elements instead of 3 compared to what we used before, but the bandwidth will be much, much larger. And with that, I did some simulation. So previously, this is basically the size of the main lobe or the main lobe itself. And we're looking at the 3 degrees of across this main lobe. And with RIFTS capability, you can see this main lobe will be smaller, a couple factors smaller. Okay, so the instrument was designed by Frank Lane at MIT Haystack Observatory. Yeah, he's a really expert on this. So we have 8 RF nodes. Then at each node, we will have different types of antennas, 3 types of antennas. And each of those nodes is connected to the core. We call it a array core through coaxial cables. So RF signals can propagate through the coaxial cables to reach the core. Then at the core, we use Xilinx RF support. It's an FPGA board to digitize the data. And the particular type of board we're using can support 16 channels. And each channel can be digitized at 2.5 gig samples per second. So it's very, very fast. And each sample is actually 2 bytes. And so we have at a recall here, we have computers, and the computer will download the data from the FPGA board, and then eventually the data will be transferred to either the hard drive on the computer or external portable hard drive. And let's move on. So as I mentioned, we use 3 types of antennas. We have LWA antennas. This covers from 10 to 90 megahertz. And we have scalar 2 antennas, covers 30 to 650 megahertz. And a broadband Erroneous monopole antenna, it covers 150 megahertz to 3 gigahertz. So we really cover a very wide frequency range. And at each antenna or at each RF node, we have front-end electronics. We have basically low noise amplifier for each antenna. This scalar 2 and LNAs, they're also designed by my co-PI Frank Lane and his team. And then we use some commercially available components to build this last omnilog LNA. This is for that small monopole antenna, covers a very broad bandwidth. At the array core, we have the digitization card and also computers. And since the intention is to make it deployable, so we have 2 racks. Our rack contains the FPGA board or RF support, and with octa-clock GPS unit, it can provide very stable, accurate GPS clocks. And we also have additional ETRS N210 radio unit that's to record another antenna I didn't mention so far. It's to cover VF to the HF range. And finally, we have a computer rack. It has computers, 2 computers, One is for data acquisition, another is for data processing. And we have network switch, and we use this network switch to build internal network so we can easily manage different devices. And this bottom figure here shows the RF board we're using. This is ZCU216, and it can support, as I said earlier, it can support 2.5 gig samples per second for each channel. There are a total of 16 channels, and there are 2 hard drives, 2 DDR4 memory on this board, and each is 4 gigabytes. And so then for this board, we will need to build an interface board so that we can interface this board with the rest of the RF system. And Franklin and his team designed this interface board for us. And so we mount this interface board here on the ZCU216. And then we have 16 channels coming in. And then they'll go through the interface board. The interface board includes LNA, additional amplification of the signal, filter, and also if we need bias to power the antenna, then it can provide a DC bias. So that is also attenuator. It's really make everything much easier. And we have this U216, and then they are placed into this enclosure, and the enclosure is designed by undergraduate student Josh, and it worked very well so far. And then, okay, so I'm going to move on to talk about the field site we're using. So we're using this piece of land here next to the UNH observatory, and it's not ideal field site for RF stuff, and when it rains, it can be really wet, and there's no one there to cut the grass. So right now the vegetation is pretty high, it's like reaching my shoulder, and we constantly have the ticks problem. And if you want talking about ticks in this field, you should ask Joe.
It was awesome. It was awesome.
And also because the grassland immediately around the observatory, they uses this land, so we cannot lay the cable just on the surface of this land. So back 3 years ago, we was dig a trench, and at the beginning, I remember it's a very hot day in the summer, it was July or August, and we rented a trench digger, a very small one, and we tried to dig a trench. It didn't work because it had raining, and the type of the mud there also is like type of clay with the grass, it just didn't work. And then we have someone from the UNH facility, Sean. Yeah, he was supposed to, every time when you bury something underground, he's supposed to mark everything, use GIS to report it. He came out to check on us a couple of times. We didn't make any progress. So then he said, "Oh, you guys should contact UNH facility." Then he actually contacted UNH facility for us. I also called. Then the next day was the same day. They brought this back home. Then they dug this big trench for us in like a couple of hours. And you can see, I think this is Steven, this is me, and this is Bobby's, I think, Anderson, and this sitting here is Ollie. Okay, in the end, we did lay down the cable for the underneath the land immediately around the UNH observatory. Then after that, then we can use, we can get the cable out, then cable just run on the surface of the land. So we install the LWA antennas and also the Omnilog, this small monopole antennas. And I mentioned we have 3 types of antenna. The third type is still sitting in the lighting lab. Okay, we still need to work on that. Okay, then before this semester started, we deployed the recall. This is like the week before the semester starts. I really want this get deployed because every time when I go to conference, people asking, when is your instrument going to come alive? So finally, we deployed it, and we have the 2 racks here. And here is the entry panels. We have lighting arresters. And so the cables are all connected, and the network is set up. So we can remotely log onto the computer, or we actually have a power switch. We can remotely log onto the power switch, then use that to turn on individual units or device and start, then we can run the instrument. Okay, so 356. A few words on the FPGA design. This is one of the most difficult projects I work on. Actually, I did the design myself, and with some help from Steven to run the hardware tests. Never worked on this before, but I did have some background on digital signal processing and also MATLAB, and but it's just very difficult. There are 3 or 4 major blocks. One is just ADC block, and one is the trigger block. Since we cannot run the instrument continuously, so we have to trigger on something. So when we have a trigger block on that, we have a block on capture the GPS time, so we can have accurate absolute timing information. And then in order to record the data at high speed or at high data rate, we decided to first save the data on the DDR4 memory on the FPGA. Then we first save the data there, then move the data to the computer. So we designed this interface for the DDR4 memory. So that's this yellow block here. Then finally, we use the board itself comes with this 100 GBE Ethernet interface. Then we use that to download the data from the FPGA to the server or computers. And I think I said that, so let me just skip that. And so this, we also developed the software by ourselves. This is mainly the work of Steven. And so we have this, when we run the instrument, it goes to, it has 3 states: monitor state, capture state, and acquire state. And so the software constantly talk to the FPGA. Then if a trigger was issued, it will wait for the trigger to be finished or the capture to be finished. Then it will set up system to receive the packets from the 100 GBE Ethernet port. And then after that, you will have to fill out the packets and then unpack the packets, because every of those packet has some headers that relate to the IP address or the port number. So you have to unpack and unpack the packets, then write the data to a RAM buffer, and this RAM buffer is entirely created in the memory. Then finally, you copy the data from the memory to the hard drive. And we also, as I mentioned, we also have antenna to cover VF to MF range. And we have N210 unit to acquire the data for that. And this is actually a work of undergraduate students. And this his name is Scott. Sorry, I forgot to mention at one of the earliest slides. Okay, so we deploy the instrument, and then let's see some data. And we did a size survey early September, and this is from the data recorded by RIFTS. So we manually trigger the system. And what you see here, okay, so this is a spectrogram. It covers from 0 to 500 megahertz. So that's the bandwidth of our instrument. And you see a lot of transmitted signals, FM bands, and also those are digital TV bands. And here is the average spectrum. Okay, can anyone guess which of FM stations this correspond to? WUAH. That's a big noise. That's a big problem for us. And so this is just a raw waveform of from one channel. So without any lighting events, we're looking at transmitted signals that are reaching 2000 ADC counts, and our ADC is like 16 bits, so it's about a factor 10 smaller than the maximum possible. Okay, so then on September 6th, there were big storms over this region. It happens to be the day of the Thunder over New Hampshire air show. And so, Stephen and I will pay attention to the weather forecast of the deployment of the instrument. And so far, until today, there are only 2 lightning storms. This is the second one. The first one, we didn't get data. And for this one, we did get the data. We get a lot of data. And during the middle of the this observation period, a few hours, I took this screenshot, and you can see the closest strike is like just 3 miles away from my house. It's very close. And okay, so then we have a total of 238 triggers. Most of them are lightning flashes, and I'm showing first 8 here, and it shows. So since we record the data, first record the data on the DDR4 memory on the FPGA with the data rate we're running. Each trigger can last at most 0.5 seconds. And so the x-axis here is just the time, and the vertical axis is amplitude, and I'm plotting the envelope. And we have 8 channels. Each channel is like 1 gigabyte of data. So I cannot plot the entire 1 gigabyte. So I decimated the data by a factor of 50. And so I still don't know what the first trigger is, but the other 7 triggers are totally lightning lightning signals. Okay, so then, so we know we got some lightning data from RIFTS, and the first thing is to validate validate our data. So I talked to a colleague at Earth Networks, and they maintain this total lighting network, and I got the data from them over the same period in this region, and I signed a non-disclose agreement, and they also asked me to promise I will use the data for presentation or paper. Then here you go. So okay, so then I'm going to show you some results and from some triggers. This is the second trigger, and this trigger turns out very close to where I live. So here is the RIFTS, and here's the Durham Point Road. I live in this region. We have 2 strikes or 2 events recorded by this total lighting network. And then if we look at the RIFTS data, here this is just overview plot. So the top left panel. So the flash will last for maybe 50 milliseconds, And then here are 8 channel, the data from 8 channels. And I'm only plotting 8 milliseconds of data for each channel. And we can analyze the spectrogram. And you can see the burst of energy that cross a very broad frequency range. Those are all lightning signals. And so here I remove the FM bands, WUNH is gone, sorry, and also the digital TV signals is also gone. Okay, so then let's see, we can use the data to find out where the source is. Then here just zoom into 1024 nanosecond time interval. This is the time interval I have been using to run the cross correlation to get the source location. So you can see even with this short time interval, we still see a lot of pulses or variation in the amplitude of the signal. So then run the.
Can I ask a question? So when I see this, oh gee, this is a tough 4D problem because the source is also moving.
Mhm.
And for your cross correlation, you have to find pulses that are alike.
Yeah.
And now they are moving.
Yeah.
So you have to have pulses that are far apart compared to the variation that you have. Otherwise, you don't get a unique result.
Yeah, so this we have, so 1 microsecond. So for 1 microsecond, if let's say the first lightning source we have seen maybe, okay, let's say maybe 10 to 7 could be a few larger than 10 to 7. So with 10 to 7, then we're talking about 1 microsecond of 10 meters. And our resolution certainly is not, it's larger than 10 meters.
Mm-hmm.
So yeah, we can safely, at least at this stage, to ignore that. But eventually, if we wanted to make, or at least for our current lightning interferometer observations, we're not at that stage to correct for that. Okay, so then analyze this 8 millisecond of data, 8 channels, then did the cross correlation, and each time window for the cross correlation is 1024 nanoseconds. The reason for 1024 is I use FFT or Fourier transform to calculate the cross correlations. That's why I use 1024. And so we're looking at the plots of elevation versus azimuth. And so the color represents time. So dark color represents early time. Light color represents more recent time. We have circles. So the circles without plus sign are TLN, the total lightning network events. There are 2 events within this time frame that are represented here. And the other symbols, those are circles with plus sign, are from RIFTS. So I was very happy to see this. So we have some sources just coincide in terms of time and location with the TLN events. And for TLN events, of course, the bandwidth is much smaller. So typically they only report a few lightning pulses, they're actually called pulses associated with each flash. So we do have agreement in terms of time and location. And this is another event analyzed. This one lasts longer. So it's almost like 400 or 500 milliseconds. Again, I only analyzed 8 millisecond time window. I pick this particular time window because there are a few, I think 3 closely spaced TLN events. So if we look at this mapping events, it turns out it's a cloud to ground lightning stroke. So we have the circles from TL total lightning network. And there is also minus sign here without any circles. Those are TLN events prior to a time window selected. It's it's basically outside of outside of this 8 millisecond time window, but we see maybe 500 milliseconds of this time period. Then for RIFTS, we have a bunch of sources. I forgot to mention the size for RIFTS sources. The size of the symbol is proportional to the intensity of the signal. So I can calculate, for example, I can pick a single channel, then calculate average intensity over this 1024 time window. Then I use that average intensity to size the symbol here. So if you have, say, a large symbol, that means during that time, during that 1024 nanoseconds, we have a big burst of radiation. So again, it looks like they agree very well. And so then, of course, I'm always looking for something different, right? So that I went through, I made the snapshot of this envelope. I put envelope for all 238 triggers. Then there are a few of them looks like this, just a single spike. It's okay. So if we zoom in, here is 500 microsecond, and then here is 500 nanosecond. Then each of those bursts is like 200 nanosecond long. And if you analyze the spectrum, it's very broadband signal. It goes from 0 basically effectively to like 500 megahertz. So I was very excited. So this is something new. And then, okay, I run this cross correlation and then do the interferometry analysis. Then the source is here, okay? And okay, so here I also show the images created by using different frequency intervals. So if we only use a very narrow band, like 50 to 85 microhertz, this is like maybe low far band. Then you can see the size for RIFTS, the size of the main lobe is relatively large. But if we use a broad frequency interval, then it becomes relatively small compared to that. And unfortunately, this is just a line on the edge of my plotting figure here. And there are other cases, and this is another case. It's just a single spike, and it's as short as this, maybe 150 nanosecond, and it has very broad bandwidth. And again, it's from the similar location. But when I was there, I actually got this last Friday. I should actually analyze another case. And then when I was looking at this, this time here is very similar to the previous events, like 2.5, 2.6. Typically I make the time, okay, so t equal to 0 corresponds to that. So if you pay attention to this is like 19, this is a UTC time, so 19 hours, 47 minutes at 27 seconds. And then this is like 1948 and 37 seconds. This is like 1 minute plus 10 seconds. So I feel like that cannot be a coincidence, but I have no idea what caused this. Right? Okay, so this is my final slide. So just a very simple conclusion, and the preliminary analysis of the first data we got confirms that RIFTS is functioning properly. It can capture ultra-wide band type data of lightning, but certainly we still have a lot of work to do to optimize the system. One thing is like related to what Eberhard asked. So ideally, when you do interferometry, you want your waveform, those waveforms from your sensors identical. If they're identical, when you do the cross correlation, then create the image, your image, the size of the main flow, the main block, and also the interference will be smaller. But if you look at this waveform here from these 8 channels, they're not exactly the same. And I think one possibility is we have a lot of trees around that sensors. At the same time, the sensor itself is above the ground, maybe about 1 meter. So we may get reflection from the ground or get the multi-path propagation, either reflect from a tree or direct wave. Then at the sensors, they will add together, so make the waveform more complex. So, but we need to understand that better. That's one thing. Another thing is, the best antenna we have is still sitting in the lab. We still need to deploy this antenna. Another thing is related to Anderson's Douglas synthesis. Anderson did a lot of measurements. So for our cables, we basically have 2 sections. First section goes from the shed to the junction box in the field. This is underground. Then the second section goes from the junction box to each individual antenna. That's the second section. And well, for the results I obtained so far, for the first section, I assume they all have the same propagation delay, but from his measurements, they're not. And for the second part, for each station, we have 2 cables. And right now, we can not tell which one is which. And Anderson only measured 8 of them. I assume whatever I was using, or whatever antenna we were using at that time during that observation period, is a cable he measured. So that also is not accurate, but in the end, we still get some agreement between RIFTS and this TLN network. So the main idea, I think the main principle works. We just need to make sure we use matched measurements to in our data analysis, then that will improve our results. Then with that, I can take some questions. Yeah.
Those weird spiky things, do you see them just during thunderstorms or are they other times as well?
So for other time, I didn't analyze so many triggers. Those maybe have how many? There are maybe like 15 of them within those 238 triggers. And for the ambient, I didn't go through so many triggers. And during that time, during that storm, airplane were flying from the air show. So I don't know whether those are some just airplane signals. But if it's airplane signal, it's very hard to imagine they can produce some signal within like 200 nanoseconds. That's really short, really short. Yeah.
I wonder if that could be from a steerable antenna, right? So you have instead of actually the dish moving in these planes, I think they steer the wavefront.
Okay.
And so as far as I can tell, they can directionally, get, really good and fast
Move that dish
movement on it. So it could just be that one of those very quick pulses from the radar hit the things. Well, I don't know if that's the right frequency range. It's also a little bit weird that it's so broad, right?
Yeah, it is really broad.
Yeah.
And I hope it's not, something generated internally. Yeah, that would be bad. Yep.
Can these antennas be used for sprites?
So for sprites, those antennas will be too fast. So for sprites, the radiation, if sprites produces any radiation, it probably covers maybe very low frequency or even smaller. So their wavelength is much, much longer. This is because at high altitude, the time scale for the discharges, electrical discharges, just becomes much, much longer. That time scale is exponentially, or is proportional to L density, so exponentially increases with, it's inversely proportional to L density, so it's exponentially increases with altitude.
I have one more question. So you showed a number of spectrograms of lightning strikes. And things. I was wondering, I mean, they all look very broadband, but is there any frequency structure, like notable frequency structure in these?
So if you look at the spectrum, and typically most of them just very flat, then just rolls off. And I haven't seen from literature. I didn't look carefully from our data. From literature, I don't think there any interesting feature reported. Joe, do you know any?
We have some stuff for the narrow bipolar events, but
That's all flats and
yeah,
flats then goes down.
yeah.
Most of them.
Well, if there are no more questions, let's thank our speaker again.
Thank you.